Welcome, everyone, to a deep dive into, I guess you could say, the queen of mathematics number theory. We're going to be talking about the worlds of integers and prime numbers and really the fascinating relationships between them that have kind of captivated mathematicians for centuries now.
It really is amazing how something as seemingly simple as just numbers can lead to such complexity and beauty.
Right.
Number theory is not just about basic arithmetic. It's about uncovering those hidden patterns, the structures that govern the very essence of numbers.
Okay, so to kick things off, how about we go back in time a little bit and imagine this ancient Babylonian clay tablet known as Plimpton 322. Now, this tablet isn't just some run-of-the-mill artifact. It's actually covered in what are called Pythagorean triples.
Wow!
You know, those sets of numbers like 3, 4, and 5 that satisfy the famous Pythagorean theorem.
Right, a squared plus b squared equals c squared.
Yeah, exactly.
Oh, it's remarkable. Plimpton 322 isn't just a list. Its complexity suggests a really deep understanding of math concepts. Some scholars even believe that it might be hinting at an early form of algebra.
Wow.
A level of sophistication that predates the Greeks by centuries.
Algebra in ancient Babylon. That's incredible. But speaking of the Greeks, their contributions to number theory are undeniable. I mean, Pythagoras and his followers were absolutely obsessed with numbers,
Oh, yeah.
especially the properties of odd and even numbers. I mean, they even built a whole philosophical system around it.
Yeah. Their fascination went beyond just odd and even numbers, though. They were really into the concept of perfect numbers,
Right.
which are numbers that are equal to the sum of their divisors. And in their explorations, they stumbled upon a groundbreaking discovery. Irrational numbers.
You mean like pi that can't be expressed as a simple fraction?
Exactly. Imagine the upheaval this caused in their understanding of numbers, because up to that point, they had believed that all quantities could be represented as ratios of integers. And this discovery forced them to kind of redefine their whole framework and draw a distinction between integers and lengths or proportions.
Yeah, talk about a paradigm shift.
Yeah.
So we have the Babylonians with their Pythagorean triples and possible algebra, and the Greeks grappling with irrational numbers. It seems like number theory was already making some serious waves in the ancient world. But what about other cultures did they contribute to this tapestry?
Absolutely. Consider the Chinese remainder theorem, a brilliant piece of mathematical reasoning that appeared in a Chinese mathematical text centuries before similar ideas emerged in the West.
Wow.
And essentially what it does is it provides a method for solving systems of what are called congruences, which is a fancy way of saying it helps solve problems involving remainders.
So it's all about figuring out a number that leaves specific remainders when divided by different numbers.
I got it. It's kind of like a mathematical puzzle.
Oh.
And it's incredible that they were exploring this concept in ancient China. And what's even more fascinating is that the Chinese remainder theorem has applications in modern computing, particularly in cryptography and coding theory.
Okay.
It's a perfect example of how these ancient mathematical ideas can have a really profound impact on our modern technological world.
It really highlights how math transcends both time and culture. We see these brilliant minds across the globe, separated by centuries, grappling with similar ideas and pushing the boundaries of human understanding. So we've traced number theory from ancient Babylon to ancient Greece and China. What happened in Europe during the Middle Ages? Did number theory take a backseat?
Well, compared to the flurry of activity in the ancient world, number theory in Europe during the Middle Ages was relatively quiet. The focus shifted towards more practical mathematics like geometry and algebra, driven by the needs of things like trade architecture and astronomy. But that's not to say that number theory completely disappeared. Scholars were still preserving and studying the works of Greek mathematicians, so the embers of number theory were still there.
So it was a period of preservation rather than groundbreaking discoveries.
Precisely. But this preservation was crucial in setting the stage for the Renaissance, when there was a renewed interest in classical learning, including the works of those ancient Greek mathematicians. And this resurgence ultimately led to a flourishing of number theory in the 16th and 17th centuries.
The Renaissance. The time of Leonardo da Vinci, Michelangelo, and Pierre de Fermat.
Indeed, Fermat, a 17th century French mathematician, is a pivotal figure in the history of number theory. Although he wasn't a professional mathematician, He was actually a lawyer by trade.
Wow.
But his passion for numbers led him to make some groundbreaking contributions to the field.
Okay, I gotta ask, what's so special about this lawyer-turned-mathematician?
Well, he was known for posing these challenging problems and conjectures, often without providing complete proofs. It was like he was scattering these mathematical puzzles for future generations to solve.
Sounds like a real brain teaser enthusiast.
Yeah.
So what were some of the puzzles that Fermat left behind?
One of his most intriguing statements was that any whole number can be expressed as the sum of 4 squares or fewer.
Hmm,
Try it out. Pick any whole number, and you'll always be able to break it down into the sum of 4 squares, sometimes even fewer.
it's pretty cool.
Ah.
It seems so simple,
Yeah.
but I bet proving it is a whole other story.
Yeah.
What else did Fermat come up with?
He also delved into the properties of prime numbers, those kind of elusive numbers that are only divisible by 1 in themselves. And he came up with what is now known as Fermat's Little Theorem, which describes a really fascinating cyclical pattern related to prime numbers.
Okay.
It essentially provides a way to test whether a number is likely to be prime.
So a primality test. That's got to be useful.
It certainly is, and Fermat didn't stop there. He also made insightful observations about the relationship between prime numbers and sums of squares.
Hmm.
For instance, he noted that certain prime numbers could be expressed as the sum of 2 squares while others couldn't.
Hmm.
And this seemingly simple observation opened up a whole new avenue of exploration in number theory.
It's amazing how just one observation can spark so much research.
Mm-hmm.
Fermat sounds like he was a real trailblazer in number theory.
Yeah.
But you mentioned that he was known for posing problems without always providing solutions. Did he leave behind any particularly challenging unsolved mysteries?
He certainly did, and the most famous of them all is Fermat's last theorem. It's a deceptively simple statement. You can't find 3 positive integers that satisfy the equation a to the n plus b to the n equals c to the n for any integer value of n greater than 2.
Okay, so it works for squares, like 3 squared plus 4 squared equals 5 squared, but not for any higher powers.
Exactly. Fermat actually scribbled this statement in the margin of a book and claimed that he had this marvelous proof, but that the margin was too small to contain it.
Oh, well.
And that little note set mathematicians on a wild goose chase for over 350 years.
350 years. Talk about a long-lasting mathematical mystery.
It was a real head-scratcher. Mathematicians spent centuries trying to either prove or disprove Fermat's last theorem, and in doing so developed new mathematical tools and concepts along the way. And it wasn't until 1995 that a British mathematician named Andrew Wiles finally cracked the code,
Wow.
using incredibly advanced mathematical techniques that Fermat couldn't have even dreamed of.
What a triumph. It's fascinating how a seemingly simple problem can have such a profound impact on the development of mathematics.
It's a testament to the power of a good puzzle. Fermat's last theorem pushed mathematicians to their limits and forced them to expand the boundaries of knowledge and invent entirely new areas of mathematics.
So Fermat was a bit of a mathematical mischief maker, leaving behind a trail of unsolved problems that captivated mathematicians for centuries. But who picked up the torch after Fermat? Did anyone manage to tackle some of these unsolved mysteries?
Enter Leonhard Euler, an 18th century Swiss mathematician often hailed as one of the greatest mathematicians of all time.
Wow.
Euler was a prolific genius. He published hundreds of papers on a really wide range of mathematical topics, and number theory was one of his passions.
So Euler was the one who took on Fermat's challenge.
He did, and with remarkable success, Euler proved many of Fermat's earlier conjectures, including Fermat's Little Theorem.
Okay.
He also tackled other number theory problems, making significant contributions to the study of Pell's equation, which involves finding integer solutions to certain quadratic equations, and he even delved into the world of quadratic forms, which are expressions involving squared terms.
It sounds like Euler was a mathematical powerhouse. Did he just solve problems, or did he bring anything new to the table?
Euler was a true innovator. He introduced powerful new tools and techniques to the field of number theory. One of his most significant contributions was his work with infinite series, which are essentially sums with an infinite number of terms, and he showed how these infinite series could be used to represent and study various number theoretic functions.
Infinite series?
Nah.
That sounds pretty mind-boggling.
It is, and Euler's work with infinite series laid the groundwork for what we now call analytic number theory,
Okay.
a branch of number theory that uses tools from calculus and analysis to study the properties of numbers.
So Euler not only solved problems, but also opened up new avenues of research.
Exactly. He was a bridge between that classical number theory of Fermat and the more modern analytic approaches that would really dominate the 19th century. He even made early contributions to the study of the Riemann zeta function, which is a complex function that has profound connections to the distribution of prime numbers and is still a major area of research in number theory today.
Wow. It's incredible how one person can have such a profound impact on a field. So we've got Fermat the puzzle master and Euler the problem solver and innovator. It seems like number theory was really starting to gain momentum by the 18th century. But where did it go from there? Did it continue to be a unified field, or did it start to branch out into more specialized areas?
That's a great question, and it takes us to the 19th century, a period that saw a remarkable expansion and diversification within number theory. Think of it like a tree with its roots in the ancient world, its trunk growing strong through the work of Fermat and Euler, and now its branches starting to reach out in new directions.
So the tree of number theory is branching out.
Precisely, and as we delve into the 19th century, we'll encounter some truly brilliant minds who pushed the boundaries of the field even further.
I can't wait to hear about them. Stay tuned as we continue our deep dive into the fascinating world of number theory.
As number theory was blossoming in the 19th century, we see the emergence of some truly brilliant minds who pushed the boundaries of the field. One such figure was Joseph Louis Lagrange,
Okay.
an Italian-born mathematician who made significant contributions to a wide range of mathematical fields.
So Lagrange was another multi-talented mathematician like Euler.
Lagrange had this remarkable ability to see connections between different areas of math. And in the realm of number theory, he proved some of Fermat and Euler's earlier conjectures.
Okay.
And he also developed new techniques for working with quadratic forms.
Mm.
He also made important advances in the study of Diophantine equations, which are equations where we're looking for integer solutions.
So it's like he was building upon the foundations laid by Fermat and Euler, taking their ideas even further.
Precisely. And alongside Lagrange, we have another influential figure, Adrien-Marie Legendre,
Okay.
a French mathematician who dedicated a lot of his work to number theory.
What was Legendre's claim to fame in the world of number theory?
Legendre is best known for his work on quadratic reciprocity, one of the most beautiful and fundamental concepts in number theory.
Okay, I have to admit, quadratic reciprocity sounds a bit intimidating. Could you break it down for us?
Of course. Imagine you're looking at a multiplication table.
Right.
Quadratic reciprocity basically describes this fascinating pattern related to squares in what are called modular arithmetic.
Okay.
It tells you about the solvability of certain quadratic equations based on whether certain prime numbers are squares modulo other prime numbers. It's a bit like a secret code embedded in the structure of prime numbers.
So it's about understanding the relationships between prime numbers and squares.
Exactly. And Legendre's work on quadratic reciprocity paved the way for deeper explorations into the properties of prime numbers, laying the groundwork for some of the most profound results in number theory.
It's amazing how these seemingly abstract concepts about prime numbers and squares can have such far-reaching implications.
It really is. And speaking of far-reaching implications, we can't forget about the titan of 19th century mathematics, Carl Friedrich Gauss, often hailed as the Prince of Mathematicians. Gauss made groundbreaking contributions to almost every area of mathematics.
Right.
And his work in number theory was particularly profound.
Gauss, the name definitely rings a bell. Wasn't he the child prodigy who supposedly added all the numbers from 1 to 100 in his head in just a few seconds?
That's the one. But Gauss's genius went far beyond childhood anecdotes. He published his magnum opus Disquisitiones Arithmeticae at the age of 24.
Wow.
And it completely revolutionized the field of number theory.
So what made Disquisitiones Arithmeticae so revolutionary? What did Gauss bring to the table that hadn't been done before?
Well, for starters, Gauss introduced a level of rigor and systematization to number theory that was unprecedented. He established many of the fundamental concepts and notations that we still use today. He delved deep into the theory of quadratic forms, expanding upon the work of Lagrange and Legendre, and he made groundbreaking connections between number theory and other areas of mathematics, like geometry and complex analysis.
So he wasn't just solving problems, he was creating a whole new framework for understanding number theory.
Exactly. One of Gauss's most remarkable insights was his discovery of a deep link between roots of unity,
Okay.
which are complex numbers that equal 1 when raised to certain powers, and the structure of what are called number fields, which are extensions of the rational numbers.
Roots of unity number fields. It sounds like number theory was starting to get pretty abstract and complex.
It was. And that's a testament to the incredible depth and richness of the field. As mathematicians delved deeper into number theory, they realized that it wasn't just about integers and prime numbers.
Right.
It was about exploring abstract algebraic structures, uncovering hidden symmetries, and finding connections to seemingly unrelated areas of mathematics.
So it was like number theory was becoming more interconnected with other branches of mathematics.
Absolutely. And this trend continued as number theory evolved throughout the 19th century. We see the emergence of distinct subfields, each with its own unique set of tools and techniques.
Okay, so we've got the tree of number theory branching out. What were some of the main branches that emerged?
One major branch is analytic number theory, which uses tools from calculus and complex analysis, like those infinite series that Euler pioneered to study the properties of numbers.
Okay.
It's concerned with things like the distribution of prime numbers, the average behavior of arithmetic functions, and the deep connections between number theory and the Riemann-Zeta function.
So analytic number theory brings in the heavy machinery of calculus to tackle number theory problems.
Precisely. And on the other side of the spectrum, we have algebraic number theory, which uses the tools of abstract algebra to study algebraic structures that are related to integers.
Algebraic number theory. What kind of algebraic structures are we talking about here?
Well, imagine you take the rational numbers and you extend them by adding in roots of certain polynomials. For instance, if you add the square root of 2 to the rational numbers, you get a new number field.
Okay.
Algebraic number theory studies these number fields and their properties using concepts like rings ideals and Galois theory.
So it's like taking the familiar concept of numbers and extending it into a more abstract realm.
You got it. And algebraic number theory has led to some really profound insights into the nature of numbers and their relationships.
It seems like number theory was really flourishing in the 19th century, branching out into specialized areas while also becoming more interconnected with other fields.
It was a period of remarkable growth and diversification. And this trend continued into the 20th and 21st centuries, with number theory becoming increasingly sophisticated and finding surprising applications in really diverse areas, including cryptography, coding theory, and even theoretical physics.
So from ancient clay tablets to modern-day applications, number theory has come a long way. But amidst all this specialization, are there any unifying themes or big questions that continue to drive research in number theory?
There are. One of the most fundamental questions in number theory, and perhaps in all of mathematics, is the quest to understand the distribution of prime numbers.
Okay.
Prime numbers, as we've discussed, are the building blocks of all integers, and their seemingly random yet patterned appearance has fascinated mathematicians for millennia.
It's like trying to decipher a secret code hidden within the sequence of prime numbers.
Exactly. And there have been major breakthroughs in understanding the distribution of prime numbers, like the prime number theorem, which gives an estimate for the number of primes below a given number. But there are still many unsolved mysteries, including the famous Riemann hypothesis,
Okay.
which proposes this deep connection between the distribution of prime numbers and the behavior of the Riemann-Zeta function.
The Riemann hypothesis. I've heard of that one, but I have to admit it sounds pretty daunting.
It is. The Riemann hypothesis is one of the most challenging and profound unsolved problems in all of mathematics. If it were proven, it would have major implications for our understanding of prime numbers and their distribution. But it's a tough nut to crack, and mathematicians have been grappling with it for over 150 years.
So it's a prime example of a problem that continues to drive research in number theory, pushing the boundaries of mathematical knowledge.
It certainly is. And beyond the distribution of prime numbers, there are other overarching themes that connect different areas of number theory, like the search for patterns and structures within the seemingly chaotic world of numbers, the exploration of symmetries and their implications, and the quest to understand the deep connections between number theory and other areas of mathematics.
It's fascinating how something as seemingly simple as numbers can lead to such profound and far-reaching questions.
It's a testament to the beauty and power of mathematics. Number theory, at its core, is about seeking order and understanding within the abstract realm of numbers, and in doing so, it often reveals unexpected connections to the physical world and to other areas of human knowledge.
Okay, so we've journeyed from ancient Babylon to the frontiers of modern mathematics, exploring the fascinating evolution of number theory. We've seen how this field, once concerned primarily with integers and prime numbers, has blossomed into this vast and diverse landscape, encompassing everything from abstract algebraic structures to complex analysis.
It's been quite a remarkable journey. And one of the most compelling aspects of number theory is that it's a field that's constantly evolving,
Right.
with new discoveries and connections emerging all the time. It's a testament to the enduring power of human curiosity and our insatiable desire to understand the underlying patterns of the universe.
I have to admit, I'm feeling a bit mind-blown right now. Who knew that something as seemingly simple as numbers could lead to such a rich and complex field of study?
It's true. Number theory is this beautiful blend of simplicity and complexity. It starts with the most basic building blocks of mathematics, integers, and from there it spirals out into this universe of abstract structures, profound theorems, and unsolved mysteries.
It's like peeling back the layers of an onion, revealing more and more complexity with each layer.
That's a great analogy. And the best part is that there's always more to discover. Number theory is a field that's full of surprises, and it's constantly challenging our assumptions about what we think we know about numbers.
So what are some of the key takeaways from our deep dive into number theory? What do you hope our listeners will remember from this exploration?
Well, I hope they'll appreciate the sheer beauty and depth of number theory, how it connects to so many other areas of mathematics and even to the physical world. And I also hope they'll be inspired by the stories of these brilliant mathematicians who dedicated their lives to unraveling the mysteries of numbers.
It's certainly been a fascinating journey. We've seen how number theory has shaped the development of mathematics from ancient times to the present day. And it's clear that this field will continue to captivate and challenge mathematicians for generations to come. It's amazing how something as abstract as number theory can have such tangible applications in our daily lives. We've talked about cryptography, coding theory, even theoretical physics. What other areas benefit from these insights of number theory?
It's fascinating how number theory kind of pops up in these unexpected places, for instance, in computer science, particularly in the design of efficient algorithms. The concepts of modular arithmetic and prime factorization are super crucial in areas like hashing and random number generation, which are fundamental to computer programming.
So even the software we use every day relies on principles from number theory.
It does. And let's not forget about music.
Okay.
The mathematical ratios and patterns that kind of govern musical harmony have intrigued mathematicians and musicians for centuries. The ancient Greeks, for example, they believed that musical harmony was deeply connected to the mathematical harmony of the cosmos.
So there's a hidden mathematical symphony within the music we hear.
There is, and exploring those mathematical underpinnings can really enhance our appreciation for the beauty and complexity of music.
It's incredible how number theory, which started with simple questions about integers and prime numbers, has expanded to encompass such a wide range of applications and connections. It's a testament to the power of abstract thinking and the interconnectedness of knowledge.
Absolutely, and I think one of the most important takeaways from our deep dive is that number theory isn't just this collection of formulas and theorems, it's a way of thinking, a lens through which we can view the world and uncover hidden patterns and relationships.
It's like a secret code that unlocks a deeper understanding of the universe.
Exactly. And learning this code, even at a basic level, can really enrich our understanding of the world around us and spark a sense of wonder and curiosity.
So where does this leave us? Was the next chapter in the story of number theory?
Well, the beauty of number theory is that it's this ongoing story, a quest for knowledge that's never truly finished. There are still countless unsolved mysteries, profound questions waiting to be answered. The Riemann hypothesis, which we touched upon earlier, continues to tantalize mathematicians, and there are countless other conjectures and open problems that'll keep future generations of number theorists busy.
It sounds like there's plenty of work left to do for those who dare to enter the realm of number theory.
There is, and with the advent of powerful computers and new mathematical tools, who knows what incredible discoveries await us in the future. Perhaps we'll finally crack the code of the Riemann hypothesis, or uncover even deeper connections between number theory and other areas of science.
It's exciting to think about the possibilities. So as we wrap up our deep dive into the fascinating world of number theory, what's the one key message you want our listeners to take away?
I want them to remember that number theory is not just for mathematicians. It's a field that's accessible to anyone with a curious mind. It's about exploring the beauty and wonder of numbers, uncovering hidden patterns, and appreciating the power of abstract thinking.
It's a journey that's both intellectually stimulating and deeply rewarding.
It is, and I encourage everyone to embark on their own exploration of number theory. You never know what fascinating discoveries await you.
Thanks for joining us on this incredible journey through the captivating world of number theory. We hope you've enjoyed the ride and that you'll continue to explore the wonders of numbers long after this deep dive is over. Until next time.